Ladies and gentlemen, welcome to the presentation on WaterSense, the European project that is trying to make sense of the water value chain in Australia. And my talk is entitled Precipitation Data in Real Time for Multiple Scale Applications in Australia. My name is Thomas Einfeld, and I'm talking here on behalf of the whole WaterSense consortium. And you can see the logos of the different organizations involved on top of the screen. So what is the background? We know that climate change is leading to extreme weather, and that the water crisis ranks in the risk report very high. Earth observation data are available and the quality continues to grow. And therefore, there is a need for tools to support efficient water management. And in particular, in Australia, there are a number of cases where this can lead to a better management. So the WaterSense vision is to address the challenges in the water domain by developing an Earth observation-based modular water monitoring system that is adaptable to user needs and circumstances. What does it mean? Our goals are to develop a modular operational water monitoring system built on Copernicus Earth observation data, so that water managers will have a toolbox of reliable information on water availability and water use. And so we are starting in Australia, but we want to go on in South Africa, Netherlands, and also other parts in the world. So the solution should be scalable for any place in the world. So the toolbox makes data and services available to users. And so here you can see that the data are coming from Copernicus, but they are also coming from meteo services and from in situ observations. And additionally, there are also other Earth observation data which currently are not available through Copernicus that we are using. Then we're having processing algorithms, and these algorithms are then producing information for different apps, like for a water auditing app in Australia for water use, but also for third-party applications. So here you can see this in a graph. We are using Earth observation data, we are using local and in situ data, and this is then through WaterSense being channeled and translated to urban managers, to stakeholders for example, for reservoirs and also for agriculture. The project objectives are to create a modular water monitoring system that is able to provide a large variety of data sets in different space and time scales. We want to develop algorithms that use and enhance Copernicus data and that give information that is then useful for applications. And we are researching and developing integrated calibration and validation methods for the WaterSense data and results. We are also demonstrating the value of the results that we are producing in close cooperation with prospective end users. We also develop business cases and flexible service subscription models for various markets and customers, including also a roadmap for the whole Earth. Our focus here in this talk is precipitation. We are first taking the best available data, which we consider being corrected and gauge-adjusted radar data. They are not always and everywhere available, so there are fallback strategies that are required. And these fallback strategies are satellite data, our station data, and our weather model data. Our case study is the Namoi catchment and Namoi radar, and this serves as a ground validation for the method development for Earth observation data and their enhancement. Here you can see the Namoi radar, the coverage of the radar, and Sydney is here on the south and just outside the radar coverage. This radar is an S-band radar, and we are working with the different elevations of this radar and correcting the data and comparing it to stations. The radar measurement is sketched here. So the radar is sending out a beam into each direction, and what is reflected is being measured here at the radar site. And then the reflection has to be analyzed, whether it is precipitation or whether it is another object, such like airplanes or windmills. You can see here on the left a radar sum of half a year before corrections, and on the right-hand side after corrections. And you see here that the fields are much smoother, and some items like this blockage here has disappeared. Finally, we are producing Cartesian data for the Namoi catchment, which is the catchment surrounded by this black line. This data is available online, adjusted to BOM, Bureau of Meteorology station data. And this is online since November last year. We are going ahead now and using also satellite data and compare them to radar, because we want to enhance the provided satellite data to get a better resolution in space and time of the satellite data. On the left-hand side, you see the radar data, and on the right-hand side, a sample of the satellite data, and you can see the different spatial resolution here. So our approach is to add station data and soil moisture data in order to get a better spatial image of the precipitation being supported by the satellite data. Application cases are, on the one hand, soil water availability modeling, catchment hydrological modeling, and detailed spatial modeling, looking into details of water systems and water infrastructure. The precipitation data, as I said, are online available for each of these modeling levels. Now, the Namoi radar since November 2020, and we intend to have for Australia enhanced Earth observation data and station data available in mid-2022 and beyond Australia in mid-2023. So this project is a research-driven consortium, mainly based on small and medium enterprises. And you can see here the different partners. And with this, I thank you for your attention, and we are thanking the European Commission for the support in this project. Thank you very much.